What we're trying to demonstrate here are the testing procedures that you need to use for to detect Phytophthora in nursery plants. Nurseries turn out to be one of the most favorable environments for Phytophthora that you can conceive of. They have high levels of moisture, they have very high root densities inside of containers. There's a very uniform plant genetics usually within a small area, because you often have the same species or the same clonal variety, for instance, growing all in blocks. There's many aspects of it epidemiologically that make a nursery environment very, very conducive to Phytophthora. So the tests that we're going to demonstrate in this video involve ways to test aggregate numbers of plants. Instead of testing individual plants, we can test them in bulk in a non-destructive way. And it also allows us a sensitivity level that's on actually the best that's available right now for testing bulk plants. And from number of tests, we can see that if we have an infection rate of something on the order of 2.5 to 5% in the lot, that would be 1 in 20 to 1 in 40, one infected plant in 20 to 40 uninfected plants. This test will typically pick that up. The principles behind how this works have been known for years. It's been known for decades and decades that you can detect Phytophthora inoculum in runoff from nurseries or from other contaminated sources. So the whole trick here is to come up with a way to take that observation and put it into some kind of system where we can optimize detection in a routine fashion. One thing nice about this test is pretty much all the components that it takes to do the test are things you can either buy from the hardware store, or in some cases you might have to order it online, but it's all pretty straightforward stuff. We use green pears as the bait. A very sensitive bait, as it turns out, and one that is, very easy to get a hold of all year round, really, it turns out. The website for the Phytophthora Working Group is calphytos.org, and that has a copy of the BMPs on it, the Best Management Practices. And it has, I think, links to our website where right now we're maintaining the protocols on that. That's the phytosphere.com website. Testing isn't the be-all and the end-all, because we don't have kind of a magic bullet test that could, we could scan the whole nursery and say, okay, there's 5 infested plants out there. I mean, there's nothing like that available. People would like to work on that, and there's some research underway to try volatiles or other things. But failing that, and the equipment that it would take to do that, this is a methodology that nurseries can use right now, and they can find out, okay, are we having detectable levels of Phytophthora, and they're detecting a level that's catches it at an early stage, well before everything's heavily infested. So what we use is the vinyl flashing sheets. We used to have 20-inch stuff. All the stuff we can get nowadays is the widest is 18-inch. This just comes in big long rolls. We make these little hooks that get caught on everything. We're just going to pass one end under the other side. You can either crawl around on the ground, which is annoying, or you can use a stick of some sort to pass it under, so you don't have to get down on your hands and knees. And I'm going to hand that off, Stitch, if you can hold that. All right, so these cords have cord locks on, these plastic cord locks, and we can adjust the lengths by varying how much length we have on held up by the cord lock or by spacing these hooks. We're showing a single array here. We'll show later how you can gang a couple of these together. We need these little PVC dams across the front. They help channel the flow. They're just a piece of lightweight PVC pipe. Only trick on these is putting them on from the end. You can't really slip them on any other way. And they'll help keep the flow concentrated towards the center there. All right, the next thing we'll need is to go ahead and we'll set up a thing in the vessel with a pair. These vessels we'll describe later on. We'll show you a little demo of how they work. But the bottom line, the drain is on the bottom and the overflow level is here. So when water's coming into it, this is as high as water will get before it pumps out. And because zoospores swim upward, we want not to have it overflow from the top. We want to have it flowing from the bottom. And we have a demo that shows that. And this is just a piece of this same flashing, and it's used to give us cut turbulence into the vessel. We don't want a lot of turbulence in there because it turns up the zoospores, which will normally swim upward. It kind of forces them back down. They can end up exiting out the drain that way. So we are trying to do everything to maximize the likelihood that the zoospores, if they're present, can actually get into and infect our pairs. A piece of stuff basically just has a couple of slits in it, and it's going to slip underneath those pipes like so, and just kind of hang there and help basically give us a sort of a water slide effect to cut that flow down into the thing if that end of the pipe is not in far enough. Right. Is that in there?
I think you need to push yours a little more forward.
All right. Okay. That's
think
tighter?
good.
Okay. All right. So when you're set up for a test, you're going to get we're using green pears as our baits, and we can explain more about that later. So anyway, this data sheet is essentially, we can look at this closely, but basically we want to make sure we have all the information recorded about why we tested, what we're testing, how we're testing it, so that we have results and they either mean something or don't mean something to us. We can always cross-check against how the test was done. This is a Danjou pear. This is a pretty nice looking one. We don't peel the sticker off because that'll rip the skin off and cause wound. This one actually has a wound on it. And so if there's some issues on a given pear, or there's some other kind of blemish and you just want to make sure that you've noted that beforehand, you can just take the Sharpie and dot a little dotted line around it. What we do try to get them as green as possible. Basically, you want them so green that you would never want to buy this to eat it because you think this is going to take a week or two to ripen. Well, that's really what we want, because we want the baiting period to actually, with the post-processing, takes a little bit over a week. So we really want that pear to stay nice and green over that whole period. Bartletts have a tendency to ripen faster, so they're a little bit less desirable unless they're super green. Danjous have a tendency to be pretty green for a good long time. So we usually prefer to use them when they're available. We do rinse them off beforehand with a little bit of like diluted dish soap, and then rinse that soap off real good, just so that there's no external residues on them on the outside. I guess one other thing before I put this in, we do want to, these pears have to float. Most pears do, but if they don't, you have to put a float on them, a PFD, a pear flotation device. And we have some in the thing there. We'll demo that later, how those go on. But the bottom line is better to check them first when you're washing them out, because you have it in here and you're running the test and you find that it doesn't float, then it's a real mess to kind of deal with it. So better to pre-float, check them, and you can just note if it's a sinker on it, put a sink or something on it, and then you'll know that's when you're going to need to put a float on. All right, so that'll sit on the bottom. All right, so as part of the documentation, you want to throw me on my camera? I know how to use that better. We would normally go ahead and photograph the material that we're going to test. We talked about the fact that we're going to low grade this material, which is we're going to look for something that might be potentially symptomatic. So what we like to do, in a way, if you're going to just photo document, it's worth it to kind of get an idea of what the whole block looked like, and then specifically the material that we're testing, and we'll just photograph that maybe once we bring it out here. So Bree's already.
But normally you would photograph the data sheet first.
Yeah, you're right. You're right. Sorry. So yes, so I know what this photograph goes with, I photograph this, and then we'll get the material over here. So Bree's already picked out some material here with various types of symptoms. What we typically were going to look for, actually we like to look for stuff that's a little bit stunty and otherwise looks like a little water stress, or like it might have some kind of chronic water stress issues. You know, if there's a little marginal necrosis here, that could be a water stress issue. It could be something else. This could almost be mechanical because of getting bumped into things or something. But in terms of testing, you do want to go through, and if you have a large batch, you're not going to be able to test every plant. So you will want to take a sample that is representative of the worst looking plants, essentially. So that way you have a better chance of detecting the pathogen if it's there. And if you've tested the worst looking ones and those tests come out clean, then you have a pretty good confidence that it's not Phytophthora that's making those plants look bad. There's some other issues in there. And that's the problem with Phytophthora. Short of knocking out the root systems of each one of these things, we really can't observe the effects of the Phytophthora is having, which is a root decay type of organism. So, and especially with plants this small, which they aren't well rooted, we'd essentially have to destroy the plant virtually to check the root system. So this allows a non-destructive test. The exposure of these to any kind of cross-contamination is really no different than they are on the bench when they're being watered. So in a way, if these tests out clean, we put them back with no harm, no foul. Basically, we're back where we started. So we've gotten then those our arrays set. So I'll go ahead and get a photograph or two, just so we have documentation, what they look like, and have any kind of questions about it later on. You at least have that as a backup. And I'll check that off on the list. And write down a couple of other things. These are going to be moved. We're using one collection sheet. We're going to use a standard zoospore collection vessel. We'll talk about another type. And write down the number of containers in the test. We have 2 racks of 20 here, so there's going to be 40 total in this test. We already talked about the fact that there's up to some point, there's not, although you can test more, there gets to be a kind of a diminishing returns on putting too many plants in the test, in that it'll take longer, you're running more water, and if you only have a few infected plants, the more non-infected ones you include in that test, the lower the chance that you'll actually get a detection. We say right now we usually have pretty good detection on an infection rate of somewhere between 2.5% to 5% of the batch. That would be one or two out of this batch here. We could detect that. Not necessarily 100% of the time, but at a high percentage of the time. So if we've already grouped kind of the worst ones together, we probably now have, more than 1 or 2 in this batch. So we have a pretty good chance of getting a detection if in fact this was an infected batch. The next bit we'll need to do, I guess, is calibrate the irrigation device. Okay, we want to apply roughly the same amount of irrigation to each one of the plants, because we don't really know which, if any of these are infected, so we're just going to give them all equal probability of being detectable. But you can see that even in this batch here, we got some things with, ½ centimeter of headspace. We've got ones with 1.5 centimeters. If we just fill them up to the headspace, we're going to be putting different amounts of water on. And if we have no headspace in virtually any of them, which we've seen in lots of nurseries, you can hardly get any water on. So we don't really want to have the test vary by how much headspace there is. And so through a number of different studies we've done, we actually have come out with a standard volume that we want to apply per irrigation. We're going to irrigate these plants 6 times at 15-minute intervals. And what we're trying to do in that process is essentially initiate zoospore release from the sporangia on roots that might be in there if these were infected, and allow those zoospores to be flushed out in the water, leach out, and be collected into the vessel below, where they will swim up and have a chance to infect the pear bait, which after we take that pear bait and incubate it for a few days, we'll start seeing lesions, visual distinctive lesions that we can tell that we've got a positive. And we can, beyond that, isolate from those lesions to actually recover the pathogen and get it identified by DNA techniques. So that's kind of the whole sequence that this is the start of. So back to the volume of water, it turns out we did a number of tests, and per irrigation, we were sizing it based off the volume of the container, the nominal volume of the container, just to give us some sort of baseline that anybody can follow. And we originally were looking, we found as we were doing these trials, it was averaging between 15 to 20% of the container volume per irrigation. So we want to kind of bracket that towards the middle of that. So we were shooting for around 17% of the total container volume per irrigation. Well, if you turns out, if you think about it, which we didn't think of initially, but across the 6 irrigations, that turns out to be essentially the container volume. 17% is approximately 1/6. Okay, so in the end, it makes for a fairly easy way to calculate. If you know what your container volume is, divide that by 6, and that's approximately your target volume. Now, those target volumes tend to be odd numbers, and it's a little bit difficult to deal with them exactly, so we're going to round them a little bit to the nearest even number that we can calibrate to. But we're at least in that bracket by targeting the center of that interval. So these are D40s. They're 40 cubic inches. They turn out to be 655 mils. So a sixth of that turns out to be roughly 110. So that's our target, and we have it on the bottom of the data sheet, 110 mils per irrigation. So each one of these is going to get 110 mils. So if you figure out that you've got 40 here and times 110, we're going to put out in each irrigation something in excess of 4 liters of water is going to process through there. We want to actually see runoff starting from or leachate starting from the start of the first irrigation. So ideally the plants are irrigated the day or two beforehand so that they're all pre-moistened, and then that's not an issue. But if they are a little bit drier for whatever reason, usually happens with larger plants that really suck the soil dry quickly, the first irrigation you may have to give it one more pulse, a little bit over the total amount, just so that you're actually getting some runoff from this first irrigation, so we actually are starting the whole sequence evenly. So we're going to want to calibrate, we want to deliver 110 mils. So how do we deliver 110 mils? Well, we're going to need a fairly slow flow rate. So we can use various types of wands that to irrigate with. This particular type of wand has a flow controller on it here, so I can control the flow here. Different wands either may or may not have this, in which case you probably want to add a flow controller of some sort right below it. Also, this type of thing has different types of spray, different types of patterns. Actually, for small containers like this, you do really want something of a bit of a stream, so that you can kind of target it right in there. A spray pattern tends to float all over. And we want to make sure that effectively all the water we're going to apply goes through the container. So it doesn't do us any good to overflow the top or to spray water in between the cells, because that's just diluting the inoculum unnecessarily. So that's part of the issue. So the next thing we have to do is kind of get an idea of how much we're delivering. So most smartphones, you can get a metronome app of some sort, and that's what we're going to use here to set our pace. We'll go ahead and set it at 75 beats per minute. That has been working for us pretty well. And I'll take that graduated cylinder. we're going to apply 110. So I have a 250 here, and I've already put a dot, little dot on my mark there, so I don't have to kind of find it each time I'm looking at this thing. I want to make sure. Okay, so there's the 75 beat per minute pulse there. And really all I have to do is figure out how many pulses it takes to get me up to 110. It's close to 4, but that looks a little fast. A little low. And this is where if you have a slightly better flow controller, it helps because it can be a little bit slow. That's high. So it's a little back and forth to try to get this. It also helps if there aren't a lot of other hoses running. If there's other hoses coming on and off, every time somebody else changes the pressure, you might have, because that's where having some flow control on, or isolating the hose that you're working with helps. Okay, bingo. That's right on my dot there at 110. We can do it one more time to make sure it's right. Pretty much right on the button there again. So at 75 beats per minute with everything set up as it is right now, I basically need to irrigate each cell for four beats or 4 clicks. So when we're ready to go, which I guess at this point we are, we'll record our initial time on the data sheet so we know when we started. If you have a 15-minute timer, you can also set it now. I don't have one right on me, but somebody could set one. Or you can simply look at your data sheet, add 15 minutes, and know that's where you're going to do it. But if you're doing something else, you would basically want to have an alarm to remind you. So we're going to get 2 clicks. Sometimes hoses expand a little bit, and you get kind of a burst when you start out, so just make sure that's not an issue. But otherwise, I probably cannot apply all 4 clicks at a time given the headspace here. So probably we'll go 2 plus 2. That would be our standard if the headspace is kind of limited. So you can see some of these, I've got plenty of room. Others, I'm kind of pushing it. Okay, so now I've only applied half the water I need for this irrigation event. I'm going to go ahead and repeat that. But you can also see why, and you can see some of these drain at different rates, so you may have to wait a couple of seconds to let some of that, a little bit that subside, but that's why it's helpful to kind of run it in a split dose like this. But you also see why limitation on total number of containers comes into play. If I'm irrigating 5 times this number, it's going to take me a long time to irrigate that whole set. So in some ways, the efficiency of the test drops off. And you can see we have runoff starting from the very first one here, so we're good. Also, and for whatever reason, this particular mix or these containers, maybe because they're earlier on, there's not as many roots, we're getting a lot of solids and a lot of crud coming out, and that's okay basically. This device essentially deals with that in a way we'll demonstrate later. So that's the process, and these start out at 12:28, so at 15 minutes from that point, which would be 12:43, we would put our next irrigation on, and then keep doing that until we've put on 6 irrigations. After the 6th irrigation, we'll wait 15 more minutes for drainage and what to occur before dealing with the pair. So that's the basic process there. And so in terms of the gloves, if I'm handling the same material, I'm not really cross-contaminating anything, but if I go to handle something else, obviously if I touch anything that was contaminated, I would clean my gloves off again. And then just periodically, just for you know, just in case you thought, you know, I don't know what I've been touching for a while. You know, if you've got gloves on, it doesn't take much to just get the alcohol on them and kind of rinse them off, and at least you feel like you've cleaned up your act again. And if you're doing this without gloves, your hands are going to get really nasty after a while with all that alcohol. So if you use gloves, you can do that. Or if they get contaminated or ripped, you can just pull out a new pair. So if we're handling between sets and we're actually handling material, we would maybe decon. Here we're up above when we're irrigating. If we were actually down, you know, we actually have to, the canopies are high and we have to kind of nerf around to get into each of them, then probably if you're switching to another set of plants, you want to go ahead and decontaminate at least spray off the head a little bit, and then run some water over it to, if you can, to rinse that alcohol off. Actually, that's a better way to do it, is like that with your, so we aren't dripping alcohol on the next plant. So, so those, you know, it's partly common sense, but it has to do with your BMPs and how you're testing arrays or range, what you're doing. If it's all within the same set, cross-contamination between the same set is less meaningful than it is between sets, because if you've got contamination in your set, you've got a contaminated set one way or the other. So. We typically like to record the water temperature, and depending what time of the year you're doing your testing and time of the day, we can have a lot of differences in what the water temperature is. Especially if we've got black hoses sitting out in the sun, the water temperature can go up a lot. First thing in the morning, the water temperature is typically pretty cool. So a handy thing is to use a non-contact IR thermometer, and we can just shoot it in there. So our water temperature is about 61 Fahrenheit. So we'd go ahead and write that down on the data sheet so we know. We will typically log the temperatures as well during the study. We can use these really cheap temperature logger type units that have an external probe on them. And normally we'd actually put them in before, so we can get the temperature of the soil before we start and afterwards. But a little logger like this, put into the soil, you can measure the temperature during the entire period. Just download it to your computer, and then you can always check, you know, you say, were we within the normal specs? So we normally want to see temperatures in a moderate range, and we'd like to see the average soil temperature no less than something like 60 to 65 degrees. Sure, we could put it in. So this should have been cleaned off. In fact, it was, but if you have any doubt about any piece of equipment you're going to put into a plant, you should always clean it off before you do so. And if not, it's got alcohol in it, so we'll rinse that off. And we'll just put that into the plant. So this one's actually reading in Celsius, and it shows our soil temperature to be 15 C right now. And by holding this button down here on this type of unit, and there's a couple of types that work pretty much the same, that starts the recording function. So now it's starting to log, and it's set to log temperature every 10 minutes. And so again, if we're going to do something like that, we would note the time that we started logging. A temperature shock or temperature change often is the impetus for triggering zoospores to release from sporangia. So that's between the water and the temperature change. It's actually generally okay if you have some changes. But we don't really want to go to really low temperatures, because some species that don't like really low temperatures might not be sporulating at all at that time of the year, so we'll have reduced sensitivity. I do have a little demo here I want to show about why we made these vessels the way we did. So we've got zoospores that are essentially swimming upward. They're buoyant, and they also actively swim against gravity, okay? So that's one of the things we want to capture. The other thing we want to capture, take that back, is some of this debris, this heavier debris could have encysted zoospores, it could have oospores, it could have little infected bits of root and stuff, so we want that as well. So essentially we want to capture the stuff that floats, and we want to capture the stuff that sinks. Okay, as we add water to a system like this, you naturally have that floaty stuff floats and sinky stuff sinks, okay, right? The problem is, as we keep adding water beyond that point, what happens to the floaty stuff is all the floaty stuff floats out. So in the end, all our zoospores would be gone that we were hoping to have infecting. I mean, there might be a few floating around. We still have the sand, which is in there, is our sinky stuff, but that's not going to be optimal. So that was the whole issue on this, is how do we maintain that floating stuff? Well, when we use this type of vessel, we've got a long column, so we can minimize overflow and maximize separation. And what you're saying is, with that amount of turbulence, we're seeing a little bit, actually some of the perlite doesn't float, so that's part of the problem here. I was going to come up with some better floaties, but I didn't come up with them. You see on the surface, most of our perlite's there. If we have a lot of turbulence going in to the system, we will knock out some of that perlite, which was showing up. So for instance, if I were to really gas it, you're going to see more perlite starting to show up in this vessel here, because we're churning this stuff over, and perlite is now coming out in big chunks. So that's why we want to keep the turbulence down low. Point is, this is where the device to reduce turbulence comes into play. I guess we should dump this out to get rid of all the old perlite. I hope you don't mind a little perlite on your floor. So the less turbulent this is, the less likely we're going to end up pulling out any kind of perlite in that. So again, the question is, do some zoospores make it through? Yeah, some are going to still be kicked down and are going to go out, but we're going to maintain most of them up here through that. And also all that sand that's on the bottom is still in there too. So our pair is also floating in this business right here, right now. And it turns out from experiments we've done, we know that during the hour and a half that the test is running, that's enough time to have infection occur. We basically taken the pair out at that point and incubate it, and we can get infection in a hot sample. We've also added a pair at the end of this cycle and put it in, taken that and done the incubation step, and we also get infection there. So both steps here are when infection can occur, so that increases the sensitivity of the test. So we want to basically make sure that both parts of it are favorable. Yep. Actually, I can show one more thing with this, is that one thing we are going to do at the end, as I mentioned, we're going to reduce the water level in this. And the reason we're going to do it the way we do this here is that we're going to pivot this, and we can, as we pivot it, we're going to drop the level, but you'll see that the perlite is still staying at the top of this water column, because at the end, we don't really want to lose all these zoospores that might still be swimming at the top. So by tilting this, we can drop the level gradually without essentially sloshing all this stuff around, and we're not losing perlite, we're not losing floaters at the top of this vessel. So on this vessel, again, there were those marks, and that's where we'll drain it down to and now we know that this whole amount will fit into the thing. And so we can just slosh the stuff on the bottom and get everything dumped in at once instead of having to sort of guess how much stuff. So it's worth making the marks on your thing. Those are 10 centimeters off the bottom. So there is a way for small volumes of material to make what we call a mini zoospore collection device. So this is our standard zoospore collection device. And you can see, if you've got volumes of water that are on the order of a couple gallons or more, you're going to want to use that. But if you're only doing some real small amount of that, you can basically set the same thing up with a plastic bag and the type of vessel we're going to use at the end to incubate the pear in. And essentially this is that same plumbing system, right? So the only trick is you're going to put it through the wall of this bag. So as it turns out, you just have a piece of so if we start about what we got there, 1.5 inches off the bottom perhaps, you can just more or less thread right through this stuff, right? And you end up kind of twisting your bag a little bit. But once you twist it around and get it back so that's up, you now have this thing plumb through the wall. My problem is that you gotta pop out the membrane, so you need a knife or a chisel or something like that, and sometimes it rips, sometimes it doesn't, but you want to make sure it's wide open there so that you don't restrict the flow. So now, if you set that up like this, you're still draining now, not quite off the very bottom, so you'll keep the sinky stuff at the bottom. You keep the edge up high, and so it'll actually start draining at this point here. So this obviously works for lower flows only. If we were dumping gallons of water in it, it wouldn't be great. But if you're going to have something that's maybe only going to be a couple liters, then you can actually incubate the whole thing right in here. So at the end, when the pear is done, what we normally do is take this off, just leave it in here, and then I have somewhere over there, we have some plugs. We put a 1/2 inch plug, just a slip plug in here, so it won't drip out of this. And then you can take that off and incubate it directly like that. So that's an option for doing smaller rates plants. Zoospores, swim on their own, and they're chemotactically attracted to these pear fruit. So there's chemicals leaching out that they can detect that this is something that they might like to eat. So they swim towards it. So that's one reason why we want to cut down turbulence, because if they're starting swimming towards it and they're getting hot, and all of a sudden Niagara Falls comes in, they get tossed all around, that chemical gradient's gone, and they're not going to find it as readily. So if it's just eddying currents, that's not going to be a problem. The other thing is zoospores can swim under good conditions maybe as much as about 10 centimeters. All right, so in this thing's only about 20 centimeters across, a little bit less. So if the pear is floating anywhere here off center or close to the center, essentially all the zoospores in there have a shot of making it to that pear. When we transfer it to the bag, we've got the same kind of situation. The surface area there is all very concentrated. And that's why we want to use this size vessel. Originally some people said, okay, well I can use a 5-gallon bucket, but 5-gallon bucket, you spread that inoculum out farther, and something on the far end of a 5-gallon bucket is not going to make it over to yours. As far as baits and multiple baits, I mean, this one, as long as they all have access to getting to it, you might as well have them all go for one. And in fact, you get better symptoms if you get mass action. Essentially, 1 or 2 zoospores can infect and cause infections for certain Phytophthora species, but those will be kind of small lesions that'll take us a while to develop. Whereas if we have a lot of zoospores on there, you'll end up with a blast of all kinds of lesions all at once, and they'll often show up very early on. So typically we kind of think about transitional steps as ones where it makes sense to do testing. So you've got stuff on seed flats there. Say you're thinking, okay, we're ready, these are big enough, we want to go ahead and transplant them. Well, that would be the time where if you wanted to do a check on them, you could easily run a test on that material. A lot of those flats might be a lot smaller, and we haven't actually calibrated for flats, but the flat would work sort of the same way as we would look at the same volume thing. So you look at the volume of the flat, and then probably you'd have to just sort of spray it over the top for that period. We haven't actually run flats. It's again, what you also really want to have is the maximum amount of root density that you're going to have at a given time of testing. Because if most of that volume is full of non-rooted soil, then you're spending a lot of water spent just sort of washing out soil without actually potentially having much inoculum. So right before you transplant, you're at maximum root density there. Right after you transplant it into things like this, you're at minimum root density. So then you want to look at where your root density is getting higher, and you're closer to a period where either you're going to transition into something bigger or it's actually closer to delivery. But it also can get kind of problematic when they get really overgrown, because we have tested stuff and it's all bushy, you've got big giant things in here, it gets much more difficult to irrigate in these things. So sometimes people space at some period. I don't know if you're likely to, in this material, whether they would be left in these full racks, or sometimes people space them out alternate cells, for instance, to give them more space. If you're going to space them, that makes it a little easier to get in there, so that might be the time to go ahead and do some testing. And typically pre-delivery is a good time to do your kind of final check to make sure that, or pre-planting. But then you have sort of the seasonal issues. If they're going to be delivered in the middle of January, you're kind of going to reach not great temperatures at that point. So you might want to actually push your pre-delivery testing mostly back towards before it gets really cold in the fall. So maybe you're doing most of it in November or October. We could do a setup to show you how you gang these things together. You're about ready to irrigate, so maybe once Liz is done with that irrigation, we'll pull out things and we'll just show you how you can piece two together. It might, again, the stuff we had used to use was 20 inches wide, and for some reason they stopped making it. So 18 is as wide as you can get now. And so if you're for this type of material, it's not too bad because you've got plenty of space. But once you're starting to get 1 gallons on there and kind of spacing them on, it starts getting pretty tight. You have to kind of do a really tight pack on there. All right, so the bottom line is when you set these up, there's you have to set them like shingles on a roof, so the one in the back drains onto the one in the front. Yep. Unlooped?
Yep. So the way these work is it won't fit with the knot at the same time. So first you stick the knot through, and then you put the little toggle through.
All right, so what she's demonstrating over there,
Like that. Then
so knot, stick. So then the main thing on these is if you don't have them angled quite right, you can get things.
the water can come out the middle, so you
Right.
usually once you start, you have to double check and make sure you have it. Everybody, as high as they go on the back end, and then
See, right now we're gapping here, so something's back end's probably not quite as high as it needs to be.
like that maybe.
Something like that. Probably the front a little lower. I'm gonna drop your front there.
Maybe like that.
So we could actually check that with like the hose. There we go, this will work. So you just want to make sure that it's set so that with water coming down, it's not going to gap out the middle there. So So we don't see any leakage at the middle seam, so that's what we want. So that's, and you can theoretically go out more. I mean, we can do 3, but typically if you're doing enough big 15s, you could go to 3, and you can get probably 15s on it, or 15 5s or something like that on a 3, which is not too big of a number to test at once. But for this purpose, if you want to say do 31 gallons, you could easily fit them on a 2-sheet thing, but you wouldn't be able to fit them on the 1. And then of course, again, these bars and stuff still go across the front. But that's how you can go. So what you can do is the blue tab ones we have here are totally untied. I mean, you can put them wherever you want. But you need one set that doesn't have those on if you're going to gang them. So you'd even take it off, or you can just sort of set them aside and have 2 sets. So pear flotation device doesn't have to be anything fancy, and it doesn't take much to float a pear. So what we normally just use is a piece of closed cell foam, so something that isn't porous. But you could use a packing peanut, you could use something else. And a rubber band, that's all it really takes. The trick is, because these pears are of course pear-shaped, it won't do it to put it this way because they'll slip off. So the main thing is you have to go down to a long axis with your rubber band. And so if you...
How many do you usually need?
Usually just 1. And what it'll do is it'll cause it to float. You drop it in and plop. With that little floaty thing will just be right at the edge of the surface of the water. So even if this turned out to be a floating pear anyway, but if it was a sinker, it would still, that's about just how it would float. So it's not a big deal. And then when we transfer the pear, we'll just take it out with its float on it, put it right into the bag. And usually I'll leave the float on. Well, you can actually record on the data sheet that used the one that had a PFD on it. So just so you know, if you want to actually know what side was up, you can either leave that thing on, or you can make a couple of Sharpie marks after it dries off, just so you know, okay, here's where the thing was. So that tells you what side's up. But that's usually not that critical. You've got symptoms one way or the other. So this is clean. I can put this on the bench for the time being. But again, now this is your biggest contamination related issues here, because you want to not adding contamination to the stuff that's in the vessel, and you also don't want to transfer contamination from the ground up to any of your other material. So one thing that means is you can't touch the bottom of the vessel when you're handling it. So we will pop this off, pull this out, and there's our pear floating on top. We can take the pear out right at this point, or we can do it later, but this is as good a time as any. And then we'll just turn this and let the water level drop until we see the marks there. And that's why we put the marks on, because otherwise it's like, okay, exactly where is that point? A little hard to tell. This water is really murky, so it really helps to have the mark, because otherwise, if you were using other kind of visual cues in there, like how far it is from the pipe or whatever, you couldn't see it because this water is just like ink almost. But there's a little black line showing. We have them on 3 sides because you're not always level, so make sure that you get a level shot. And basically that means that'll all fit in there. So we don't want to dump it this way because we'll have water coming out the outflow, so we want to grab it from this side. You move that flap over. And we're going to go ahead and pour it in. And then to make sure all the stuff at the bottom comes, we're going to give it a little swirl at the end to get as much of the crud off the bottom of the vessel. A little shake. And so we've got delivered most of the material. Little crumbs are behind, but we've got so much of it, it won't matter. And there is what we're going to incubate. Now, so now this is dirty on the bottom. We can put it into some other kind of container that later on we'll have to sanitize. If you if you were right next to your incubation chamber, you could just go ahead and move this right in, but you're not typically. So for transport, we'll normally seal it. So we're going to go ahead and zip it up. When you do that, you still want to include as much of an air bubble as possible. Sort of like when you're taking goldfish home from the store, you want that little air in there. Same kind of thing. I mean, they are aerobic organisms. So we can transport it like that, and then when you incubate it, you'll pop that back open. And if you have that open and upright, it won't, we're at the level where it won't spill out. These containers, obviously just cut off bleach containers. If you're going to do that, they're cheap because you're always using bleach. But leave about a centimeter above that little line there to get it high enough. That's about as high as you can go before the bleach container sort of tapers. We've got the pear incubating here. You're going to pull it out. If it's got perlite and crud that's been floating in the stuff, it will be a little messed up looking like this. So with add a sink or whatever in your thing, you're just going to go ahead and just rinse the debris off on it. You don't really want to scrub the pear or anything fancy like that. You just want to get it cleaned off like that. And it'll be a little slimy if it's been floating around there for a little while, but that's not a big deal. And then this gets put on something. We don't have one of those bubbles right here. So typically we'll use a clean paper towel napkin and just set it on that so it'll dry. There's 2 incubation periods, one in water, and then the post water on dry.
Okay.
And then again, we probably still leave it in the chamber. And if you had ambient temperatures that were in 65, 75 range, you could just leave it at room temperature out somewhere else. But if you've got a chamber anyway, once you've done the water phase, you've suddenly got all that space cleared out in your chambers. These then compact down to a much smaller array. You can just let them sit in there like that. Move these from incubation after 3 days. That's about the first time you might see symptoms. Typically, 3 days is the minimum time it takes for symptoms to show up. Occasionally, it'll be slightly less than that. But typically, you'll pull them out, and there can be, at the water line, by that point, there can already be a line of lesions. But if the pear has been pretty much submerged, the lesions actually develop from oxidation of the necrotic tissue. So all the parts that are underwater won't have oxidized. They may look just a little funny. You'll see a slightly yellowish color or something like that. If you leave that pear out within an hour, actually within 15 minutes, you'll see it start to change color. It's sort of like a photograph developing, if you ever used to develop photographs in the old style. But basically, they'll darken progressively very quickly from those lesions if they're already established, and that's just straight oxidation. They aren't really growing that fast; they're already there. But you can also take out a pear that's perfectly clean looking, no lesions on it, set it out there, and a day later you'll start seeing that there's some lesions. So those are probably ones that developed. They're developing there, but they just hadn't expanded far enough that we're starting to get lesions developed. And they will, a few lesions on a pear will, by the time you're done with a week, can cover most of this pear. So they can really expand. Lesions on the Phytophthora tend to be firm, can be generally kind of dark brown, but they can be kind of lighter brown. And they're typically very shallow. So when you actually peel off the edge of them, we're isolating it. The pear fruit beneath it, at least on the early lesions, can be quite sound. I mean, it won't really have moved into that very much. And if you actually do a slice, you'll see that there's just the skin really, the epidermis is really what's mainly affected. Now, the other types of organism we can get in here is Pythium. That's common in nursery stock and lots of other environments. And it can infect pears, but only through wounds. So like this big wound on the bottom, that's the issue for using that is we can if there's Pythium around, we can almost guarantee that we're going to end up with some kind of Pythium infection at this wound because it's such a large one. And Pythium infections tend to be softer, and they tend to go into the flesh of the pear more readily. So it'll get fairly mushy there right away, and often it'll be kind of sunken right immediately, whereas the Phytophthora lesion is very superficial, and after a long enough time it will soften and kind of get sunken, but initially It's very firm and superficial. And again, there can be, sometimes it's really easy to distinguish between them, other times not. The different Phytophthora species vary a little bit on the reactions on pairs. But the classic ones are kind of what I've described, and that's what you'll see a lot of the time. When we're handling bleach, you're probably good to have your face shields and stuff available. We don't need a lot. Bleach is best made up fresh because the solutions, it's not stable over long periods of time. So if I make up 2 liters and I'm using 6% bleach, that takes 200 mils of bleach per 2 liters. So I'm going to add that in. And so we've got something we can spray stuff off with at 10% bleach. Take these off. It's still kind of a 2-person job up to a point. I mean, at this point it's contaminated, so the main point is that we just want to avoid more dragging on the ground than is necessary. But we really, if you were going to, if this is our testing area, whatever contamination we have is already in this area, so that's going to, yeah, okay, so if somebody's going to have contaminated hands, better to have somebody with clean hands. Adjust the water pressure, put it onto shower instead of the stream.
Is that straight up?
One more, there you go. And probably increase the pressure a little bit. Because again, bleach doesn't work very well if you've got a lot of stray organic matter to deal with. So you want to rinse all the loose crud off. We can take these off. So with the minimum of splash, you want to at least get the material off of it. So what you want to do is make sure it's wetted down thoroughly with the bleach. Now we're starting to get wind in here, so it might actually make sense for this operation to move to a, if you have a dedicated washing area or a dedicated dedicated testing area, to move to there, because with the wind blowing, these things are problematic. But basically, we'll go ahead and use 2 ways to do this, are either to be able to support it off the ground, spray it down with bleach on both sides, then you can coil it up and let it sit to give you long enough contact time. The other option is if you just put that bin on the table for a second, is we can fill this with a bleach solution, a few inches, 10%, and then we can both coil this up in it. Put these things in there, and using better gloves than these, using regular bleach gloves, we can go ahead and swash that through. Then once it's bleached, transfer it back into this, let it sort of sit for contact time, and then at the end rinse the bleach off. So the main thing is, this is kind of a sloppy operation, so you have to really kind of think, okay, if my hands are contaminated now, there are a lot fewer things I want to be touching, so it's probably better for a 2-person operation, or have your alcohol really ready to do things and move stuff around. But that's, I mean, because you are working on the ground besides just the leachate, I mean, you're having to deal with the most level of contamination that you're dealing with in the whole operation. So that's kind of important to kind of think about where your stuff is, stage it, and have it ready so you can handle it in a clean way.